Hi everyone, in this video what I'm going to do is use the Gram Schmidt process to create an orthogonal basis for a subspace of R3. We're given that the subspace is spanned by a certain set of vectors, and we're going to use the Gram Schmidt to create an orthogonal basis. After that, we'll answer the question of whether certain sets, certain vectors are in that subspace or no. And once you have an orthogonal basis, that's much easier to answer. So let's start the process. The way you do it is the first vector in this basis will be exactly the first vector that you have in your spanning set there. Okay, so x1, I'll use the letter x size for the orthogonal basis that I create. So x1 will be w1. Okay. Okay, so clearly you'll have that the span of x1 equals the span of w1. Okay. All right, so next, that's our first vector. Next, we will create the vector x2. And that vector x2 will be orthogonal to x1. Now, how will we do that? Let's look at this picture right here. Okay, so this yellow line depicts the span of x1, which is the same as the span of w1. And here's the vector w2. What we look at is the projection of w2 onto the span that will give us this squiggly coral colored vector. Okay, and we look at w2 minus that projection that will give us the x2. So you know when you write down the projection like this, you've written w2 as the sum of two vectors, one in the span and one in the orthogonal complement of the span. So this will be the orthogonal complement of the span of x1, so x2 will be orthogonal to x1. Okay, so x2 will be w2 minus the projection of w2 onto the span of x1. And I'm writing x1 and not w1 because at this stage it doesn't matter, but later on you'll see when we have more vectors here, it's more helpful to have an orthogonal set here to find the projection. Okay, so the formula for this will be w2 minus x1 dot w2 over x1 dot x1 times the vector x1. Okay, all right, so let's write this down. What is the vector w2? Negative 2, negative 8, 0, 2. 0, negative 2, right? And, let me write this also. The vector x1 is 1, 2, negative 2, 0. Okay? All right, so this minus w2 dot x1, what is that? It's minus 2 minus 16, okay, over x1 dot x1, which is 1 plus 4 times the vector x1. Okay, so what is this? This is negative 18 over 9, so that's, this part is negative 2 with the minus in front. It's minus 2 minus 8, 0, negative 2, plus 2 times that. So you get the vector 0, negative 4, negative 4, negative 2. Okay, so that's your vector x2. All right, And so now what happens, the way we've created it, because x2 is in the orthogonal complement of the span of x1, x2 is orthogonal to x1. Okay, so x1 and x2 are now orthogonal. Okay, so now how about x3? x3 will be W3 minus the projection of W3 onto the span of x1, x2. Okay, so take a look at this picture. You have W3, this set below this, what I've depicted by this purple boundary, the space enclosed in that purple boundary, or not really enclosed because it's a space, subspace of course, but I'm trying to depict the subspace span of x1, x2, and w1, w2 right here. Okay, so w3, look at the projection of w3 onto this space. Okay, that will give this squiggly purple vector. And then w3 minus that will give you this dotted vector x3. And you know that you can write w3 as a sum of a vector in this span plus a vector in the perp of that span. So you know x3 is perpendicular to the span of x1 and x2. So x3 is perpendicular to x1 and it's perpendicular to x2. If you create x3 like this, okay? And how do we find this projection? Well, since you have x1 and x2 are orthogonal, this projection is easy to calculate. And how do we do this? Let's write this down. It'll be W3 minus, what is this projection? Because x1 and x2 form an orthogonal set, it will just be this. The projection onto the individual spans or the individual vectors, if you want to call it that. Okay, so let's write down what is W3, negative 1, 13, 26, 12. Okay, that is W3. Then x1 is 1, 2, negative 2, 0. x2 is 0, negative 4, negative 4, negative 2. Okay, all right, so just so that we have it right there in our calculation. So it is negative 1, 13, 26, 12. That is W3. Minus, what is x1 dot W3? It will be minus 1 plus 26 minus 52. Plus 0 if you want to write that. And then x1 dot x1 is just 9. Okay? And then we put in the vector x1. Okay? Plus. Now what is x2 dot W3? Let's write that down. You'll have 0 minus 52, that's negative 14 times 13, negative 4 times 13, then negative 4 times 26 will just be the double of that, so minus 104, and then negative 2 times 12 is minus 24, over x2 times x2 will be 16 plus 4. Okay, I'm going to move this over a little bit. Okay, and we need to put in the vector x2 over here. Okay, now let's get rid of this. Okay, so let's calculate what do we have here. Okay, minus 1, 13, 26, 12. Okay, let's see, what's the numerator over here? Minus 53 plus 26, so it's minus 27 over 9. So that's negative 3 times this vector will be minus 3 minus 660. Okay? Excuse me. And how about this? Let's see, you have minus 156 and 24. So you will have a minus 180. The numerator is minus 180. What's the denominator? 32 plus 4, it's 36. And we know 36 times 5 is 180. So this is a minus 5. So minus 5 times that vector will be 0, 20, 20, 10. Okay? The reason I have taken care to write an extra step is because it's very easy to go wrong with signs here if you don't properly use parentheses or don't, carefully do this step by step. Okay? So let's take a look. So you'll have, this is negative 3, 14, 26, 10. That's this vector. So this is our result. And the vector we have is 2, minus 1, 0, 2. Okay, so that's our x3. And we have that the span of x1, x2, x3 is the span of W1, W2, W3. And even if you had this in higher dimensions with even more and more vectors, that continues. As you create one more vector with Gram Schmidt, the span of that set is the same as the span of those same corresponding first K vectors from the original set. Okay? And you have that this set is orthogonal. Okay? So we have that W is the span of first vector was, what do we have? 1, 2, negative 2, 0. Second vector is 0, negative 4, negative 4, negative 2. And you can check that this is an orthogonal set. Okay, we're calling this x1, this is x2, and this is x3. So just do a quick check when you do this kind of a problem because it's easy to see 0 minus 8 plus 8 plus 0. So that's x1's orthogonal to x2. Okay, 0 plus 4 plus 0 minus 4. So that is also, the sum is 0, so those are orthogonal. How about the first and the last? 2 minus 2 plus 0 plus 0. So that's also orthogonal. So that's an orthogonal set. And this is an orthogonal set. And it's a basis, of course, because all orthogonal sets are linearly independent. But anyway, you have that x1, x2, x3 is an orthogonal basis for W. Okay? So that's it. That's Gram Schmidt. And if you had more vectors, you just continue on with a minus and there's an extra term in there. Okay? All right. So now let's answer the next question. We want to use that basis to find if The vector u is in W and the vector v is in W. Well, we have an orthogonal basis for W, and you know that when you have an orthogonal basis for a set, it's easy to write a vector down in terms of the coefficients of the set. So let's actually look at what the projection of u onto W is. W is the span of x1, x2, x3, and this is orthogonal basis. Okay, so it's easy. What will that be? It will be x1 dot u over x1 dot x1 times x1 plus x2 dot u over x2 dot x2 times x2 plus x3 dot u over x3 dot x3 times x3. Okay, so it's easy. We have all our vectors here. So what is u dotted with x1? Let's write this down. 6 minus 12 minus 40 over, what is x1 dot x1? 1 plus 4 plus 4. Okay, plus. What is x2 dot u? Let's write that down here. It will be 0 plus 4 minus 80 minus 32 over 16 plus 16 plus 4. Okay, times a vector x2 plus, what is x3 dot u? Let's write that down next. It will be 12 plus 1 plus 0 plus 32, right? 12 plus 1 plus 0 plus 32 over 4 plus 1 plus 4 times the vector 2 minus 1, 0, 2. Okay, so let's see what this projection is. This is minus 52 okay, over minus 52 plus 6, so minus 46 over 9. What is this guy? You have a 36 in the denominator. What do you have in the numerator? You have a negative 108. And that is 3 times. So this is minus 3. Let's see, what do we have here? 44 plus 1, 45 over 9, 5. You have that, okay? Oh, there's a little mistake in the calculation of x1 dot u. So let me just fix that. x1 dot u will be 6, 1 times 6, plus 2 times negative 1, which is minus 2, plus negative 2 times 20, which is minus 40. Okay, so this is minus 36. It's much nicer. So that's negative 4. Okay, so let's calculate what this vector is going to be. It's minus 4 plus 10 as the first spot, minus 8 plus 12 minus 5 is the second, 8 plus 12 plus 0 is the third, and then 0 plus 6 plus 10 is the fourth. What is that turn out to be? 6 minus 1, 2016. Okay? And if you see, oh, this is exactly equal to u. Now, since you have that the projection of U onto W equals U, it means that U is in W. Okay? Different things. If the projection of U onto W is 0, it would mean that U is in W perp. Okay? These are the extreme situations. If it's some non-zero vector not equal to U, it just means that part of it is, you can think of it as, you can write it as a sum of two vectors, one in U and one in W and one in W perp. Okay? So that was the answer to 1. And how about the answer to 2? You do the same kind of thing. You look at the projection of V onto W, all right, which is V dot U1 over U1 dot U1 times U1 plus V dot U2 over U2 dot U2. Sorry, I am writing this with wrong letters. Should be X. V dot X2 over X2 dot X2 times the vector X2 plus V dot X3 over X3 dot X3 times the vector X3. Okay? So let's look at what these dot products are. V dot X1, what will it be? 0 minus 2. So minus 2 minus 34. So minus 36 is in the numerator. And 9 is in the denominator. We know from here, up here. Okay? Okay. Then let's look at V dot X2. What will it be? It is 0 plus 4. Okay, that's 0 plus 4 minus 4 times 17. Right, okay. And you have a minus 2 times 22 all over 16 plus 16 plus 4. Plus, let's look at what V dot X3 is. It is, these are easier numbers. You have 0 plus 1, so 1 plus 0, 1 plus 44, so it's 45 over 9 times this. Okay, so let's calculate what is this. So that is all right, and what is this? Let's see. So this will be 4 times 16. So minus 64 minus 44. So that is minus 108 over 38. So that will be a negative 3. And this is a 5. Okay, so add all this up and what do you get? 6 minus 1, 20, 16. And is this equal to V? No. So since the projection of V onto W is not equal to V, V is not in W. Okay? Now, if I asked you, is V in W perp? Well, since the projection of V onto W is not equal to the 0 vector, we have that V is not in W perp. Okay? Okay, so I hope that made sense. The main thing of caution over here is to get the formula right, to when you're looking at these projections to use the new x vectors, okay? The only old vectors that appear are the W3 there, the W2 there, the W1 there, and so on. Everything else, you're using the new ones you've created in the previous step, okay? And just be careful with the calculations. Very easy to go wrong, so just be careful. Use space, maybe write extra steps with the vectors, and be careful. That would actually save time. You know, me writing this extra step here actually saves time by me not going wrong and not ending up with a vector that doesn't work. Okay, so I hope this made sense to you, and good luck. Okay, bye-bye.